Okay, so now we understand that. Let's go back and look at moist convection in more details. So it starts very similar to the dry convection. We have heating at some point on the surface. So this could be the sensible heating from the surface, heating that surface air, and that surface air therefore rises as the plume. But we know it's also got moisture in it, and as it rises, that moisture is getting closer and closer to saturation. And when we hit this lifting condensation level of about 600 meters, that moisture starts condensing into clouds and ultimately into rain. And so we start getting rainfall and clouds at this 600 meter level. Now, of course, what happens then is as you get that condensation, we're releasing heat into the air. So we have this extra heating of the rising air due to the condensation. And so that is accelerating the plume further. And so the plume keeps on rising up. And as it rises up, of course, the air is getting colder. So the plume condenses more. So you get more clouds and more clouds up here. And as it condenses more, it puts more heating into the plume, and the plume rises faster and faster. And so you get this very rapid, very energetic ascent of this plume due to this continual feedback that's heating the air. Now, there's only so much moisture, so eventually it runs out of moisture to condense, and the plume is essentially dry. And therefore, it doesn't have an internal source of heating. So again, eventually that's going to reach a neutral buoyancy level and spread out away from the rising plume and sort of dissipate out. And then again, it's the same as we had in dry convection. So at this point, we just have this relatively dry, clear air, and this is radiatively cooling to space. And as it does that, of course, it sinks in these broad descent regions back down towards the surface. When you're in contact with the surface, the air warms and moistens again, and the whole thing repeats. So this is the picture of moist convection. Now, as I already suggested to you, this moist convection process is much stronger, much more vigorous than dry convection, because you have this huge additional source of buoyancy, additional source of heat, due to this latent heat release when you have the condensation. So this moist convection process is what's responsible for most of the extreme weather and dynamics you see in the atmosphere. So if you think about extreme events like hailstorms or tropical cyclones, they're all underpinned by this moist convection mechanism, this transfer of latent heat from the ocean to the atmosphere at height, which drives these very vigorous flows. To give you an idea of what a moist convection looks like in a realistic scenario, here I'm showing you results from a high-resolution convection resolving simulation over the ocean surface. So here you have a transect of a region of the atmosphere with vertical height here from the surface at zero and horizontal distance here. And this is what we call in modeling a reentrant domain. So anything that flows out one horizontal side comes back in the other side. I'm showing you 4 different fields here. So I'm showing you the relative humidity. And as you can see, it's large at the surface. It's particularly large in these bands. So this is actually an ascending plume where it's saturating. And then it decays off as you go to height. So by the time you get into the lower stratosphere, there's essentially a relative humidity of 0. I'm also showing you the cloud water. So this is just showing you where the clouds are forming and how much moisture is in them. And you'll see beneath those clouds, you've got active rainfall falling back to the ocean surface. In addition, this bottom panel here is showing you the radiative heating. And as we argued previously, pretty much throughout the entire troposphere, you have this radiative cooling of about 2 kelvins per day that's causing the gradual descent of the air. The exception you'll see is beneath the clouds, where they tend to insulate the atmosphere from being able to cool to space, and so you get essentially no radiative cooling beneath the clouds. So let's have a look at what that looks like if we run it. So you'll see you get these periodic pulses that just came through like then, which are the formation of these plumes at the surface, forming these clouds, and then the plume dissipates, and then another one comes along sometime later.